Picture this. An aircraft is grounded in Frankfurt because of a broken titanium bracket. Every minute it sits on the tarmac costs thousands of euros. Or imagine a neurosurgeon preparing for surgery tomorrow, and the patient needs a cranial implant shaped exactly to their skull. In both cases, additive manufacturing, or metal 3D printing, can deliver the part, one-off, on demand. But here's the problem. In aerospace and medical industries, every single component must be certified, and the certification process often costs more than the part itself. So the big question is this: how can we reconcile the flexibility of making unique, one-off parts with the high cost of qualification and certification in regulated industries? That's what we're unpacking in today's episode. Let's start with the fundamentals. Aerospace and medical devices are high-stakes sectors. If a part fails, people can die. So regulators demand absolute proof that every component is safe and reliable. The certification system we've inherited was built for traditional manufacturing. Think casting or forging. You qualify the process, you qualify the tooling, and then you churn out thousands of identical parts. The cost of certification is spread across that entire production run. Now compare that with additive manufacturing. Its biggest advantage is uniqueness. Every part can be different, optimized for weight, tailored for a patient, or produced on demand as a spare. But that flips the economics upside down. Certifying each geometry one by one would mean destructive testing, metallurgical analysis, and endless documentation. Imagine spending 200,000 euros certifying a spare that's worth 2,000. That's just not commercially viable. And yet, the demand is real. Airlines need spare parts on demand. Surgeons need implants tailored to individuals. So the challenge is clear. One-offs are technically possible, but financially impossible under the old rules. So if certifying every individual part is commercially impossible, what's the alternative? This is where the industry and regulators are beginning to shift. Instead of certifying every single geometry, the focus is moving towards certifying the process itself. What does that mean in practice? It means that if the machine, the material, the powder, the parameters, and the post-processing steps are all locked down and validated, then any part made within that envelope is trusted to be compliant. Think of it like baking bread. If you've qualified your recipe, your oven, your flour supplier, and the baking time, then you don't have to recertify every single loaf. Each one might be a slightly different shape, but the process guarantees it's safe to eat. Let's look at a concrete example. Lufthansa Technik and premium AEROTEC worked together to produce a titanium engine bracket, known as the A-link, using additive manufacturing. This wasn't just about printing one bracket and saying, "We're done." They went through a rigorous process qualification, proving that the powder bed fusion process, with specific parameters and a HIP cycle, could consistently produce material that met aerospace standards. The result? In 2021, that bracket became the first flight-approved, EASA-certified load-bearing metal AM component installed on an aircraft engine. That milestone wasn't just about one bracket. It showed that once the process chain is validated, future spares made under the same rules can also be certified. And it's not just Lufthansa. Companies like Materialise have taken a similar approach. Their facilities are EASA certified to Part 21 standards, meaning they can produce aerospace parts under a controlled, qualified process chain. If a customer comes in with a new geometry, say a cabin component, it doesn't require starting certification from scratch. The heavy lifting has already been done at the process level. Even machine manufacturers are building frameworks around this idea. EOS, for example, uses a 3-stage qualification system: installation qualification, operational qualification, and performance qualification. In other words, you prove the machine is set up correctly, you define the process window, and then you show that real parts produced in that window are consistent. That way, you qualify once and reuse that qualification across many different geometries. So, while it doesn't make certification cheap, it makes it reusable. Instead of paying the full price every time you print a new part, you're leveraging an already qualified recipe. And that's the critical shift that makes one-off parts possible in regulated industries. Now, certifying the process instead of every part is the foundation. But it's not the only way the industry is making one-off additive manufacturing parts viable. There are a few other strategies that work together to close the gap between flexibility and regulation. The first is something called the digital thread. Think of it as a digital paper trail that follows a part from the moment it's designed, all the way to when it's delivered. Every step is captured. The CAD design, the slicing file, the build logs from the printer, the batch number of the powder, the in situ monitoring data, the heat treatment, the inspections, everything. For regulators, this creates confidence. Even if the geometry changes from part to part, they can see the entire genealogy of how it was made. Instead of destructive testing on every one-off part, which would obviously destroy the part you need, the regulator can trust the process, because the data proves it was built under controlled conditions. It's like having a black box recorder for every component that comes out of the machine. The second approach is risk-based certification. Not all parts carry the same level of criticality, so why should they all be certified to the exact same standard? Take Aerospace. A simple cabin bracket that holds up a tray table is not the same as a turbine disc in an engine core. In medicine, a temporary surgical cutting guide is very different from a permanent load-bearing hip implant. Regulators are starting to scale the requirements to match the risk. For lower criticality parts, certification pathways can be faster and less expensive. For life-critical components, of course, the full weight of qualifications still applies. This proportional approach allows certain one-offs, like non-critical spares or surgical guides, to be produced viably without drowning in certification costs. The third solution is to use standardized building blocks. Instead of qualifying every new geometry from scratch, you qualify the basic elements once. In medical implants, this often takes the form of pre-approved lattice structures. The lattice might be certified for strength, porosity, and biocompatibility. Then, when a surgeon needs a patient-specific implant, engineers adapt the outer shape to fit that individual, but the internal lattice is unchanged. The regulator sees this as a modification within an already qualified framework, not a whole new part. The same idea applies in aerospace with base materials or with standardized process envelopes. Certify the building blocks, then remix them digitally for each unique application. And finally, there's the idea of centralized qualified hubs. Companies like Lufthansa Technik or Materialise have gone through the painstaking and expensive work of certifying their entire process chain, and from powder handling to printing, heat treatment and inspection. For customers, that means they don't have to build a certification system from scratch for every single part. They can simply plug into the hub. Need a certified spare? Send the design to Lufthansa's AM Center, and it's produced under their validated process. Need a patient-specific implant? A hospital can work with a certified medical AM provider that already has the approvals in place. By centralizing the certification effort, the cost is spread across dozens, even hundreds of clients. That's what makes one-offs commercially viable. You're not carrying the full burden alone. So when you put all of these strategies together, digital traceability, risk-based certification, standardized building blocks and centralized hubs, you start to see how one-off additive manufacturing parts can survive the very real pressures of regulation. They may never be as cheap as mass-produced items, but by reusing validated processes, scaling requirements to risk, and sharing infrastructure, the industry is finding ways to make unique, on-demand components both safe and economically feasible. So where does that leave us? On the surface, one-off additive manufacturing parts and strict certification rules look completely incompatible. Printing a single spare bracket or a patient-specific implant sounds great until you see the qualification bill. But the industry isn't solving this by making certification cheap. It's solving it by making certification reusable, by validating the process once, by building digital threads of traceability, by scaling certification requirements to match part criticality, by standardizing building blocks, and by pooling resources through centralized qualified hubs. One-off parts become not only technically possible, but commercially viable. That's the real shift. Additive manufacturing gives us repeatable uniqueness. Every part can be different, but each one is made within a trusted, validated framework that regulators accept. Now, I'd love to hear from you. Do you think regulators should make it easier and cheaper to certify one-off parts? Or is keeping the bar high the only way to maintain trust in aerospace and medical applications? Share your thoughts in the comments or message me directly. I'll feature some of your insights in a future episode. Thanks for listening.